All right, guys. So, welcome again. And in today's class, we're going to be talking about parametric equations or parametric functions, how to actually carry out their differentiation. Now, the rule that governs differentiation of parametric functions is actually what the chain rule. Simply because in parametric functions, we have the both given functions being a function of a different function altogether. For instance, if I have x to be a function of t, and I also have y to also be a function of t. Okay, so this is actually a parametric function. Instead of y being a function of x, so we can find the y dx, I'm having y to be a function of t and x also is a function of t. So which means, like I said, if x is a function of t, it means that I can only differentiate x with respect to what t. And also, if y is a function of t, it means I can also differentiate only y with respect to t. And if I carry out the derivative, the only way to find the y dx is by what? Simply multiplying these two derivatives, but at least taking the inverse of what? The x dt to become the t all over the x. That gives me the y dx. For instance, I can simply have here that the y all over the x is simply equal to, first of all, the y dt. Okay, so you notice that if I multiply by dt all over the x, dt cancels the t, I'm simply left with the y all over the x. So the law that governs the differentiation of every parametric equation is simply what? The chain rule. Okay, parametric equation actually comes when we have both functions to be a function of different variables. And I've always explained that when you have a function to be a function of another function, of course, we employ the chain rule to differentiate. So without further ado, let's get straight to a question. So let's say I have y to be equal to sine 80 and I have x to be equal to cos bt, where a and b are all constants, and I'm asked to find the y all over the x. So from here now, y is a function of t, also x is a function of t. B and a are simply constants. Okay, they can assume any value. All right, so since y is a function of t here, it means I can differentiate y with respect to t. And if I differentiate y with respect to t, if I differentiate sine, of course, from the shortcut approach to differentiate a trigonometric function, I always say differentiate the angle in front of the trig function, use the value of that derivative to differentiate, to multiply by the derivative of the trig function itself. So if I differentiate at with respect to t, I will simply have a. Since t is just to the power of 1 here, I will simply have a. So use a to multiply by the derivative of what? Sine. If I differentiate sine, I will simply have cos. So this gives me cos a t. So this gives me the value of dy dt. Also, from here, I can differentiate x, the x with respect to t, the x dt, and that's equal to the same thing. Differentiate the angle in front of the trig function, use that derivative to multiply the derivative of the trig function itself. So if I differentiate bt, I will simply have b, use b to multiply by derivative of cos. If I differentiate cos, I will simply have minus sine. So this gives me minus b sine b times t. So this becomes dy dt and it becomes dt dx. Therefore, to obtain the y dx, notice now that the y dx is actually the product of dy dt multiplied now by the inverse of what? The x dt, instead of the x dt becomes the inverse. Inverse is simply what? Dt all over the x. So from here, dt cancels the t. Of course, I'm left with dy all over the x. And this is now equal to the y dt gave us a cos at, put it down, a cos at multiplied by dt dx. Of course, dx dt gave us minus b sine bt. So which means dt dx becomes the inverse, and that's simply minus 1 all over b sine b. So simply taking the inverse of what that function, that gives you dt dx, and therefore dy dx is now equal to, so this simply gives me the whole of this multiplied by minus 1 is simply minus a cos at all over b sine bt. And of course, you can leave your answer as this. So this becomes the final answer to the given problem. So that's how you differentiate when you have a parametric function or a parametric equation. Let's consider another problem and see. All right, so let's consider that we have y to be equal to exponential t squared plus 5, and we have x itself to be equal to exponential t, and we are asked to find dy all over the x. So both ways, of course, y is a function of t here, and also x is a function of t. So which means I can differentiate y with respect to t. I can also differentiate x with respect to t. So let's do that and see. Differentiating y with respect to t from the rule of from the shortcut approach to differentiating exponential function. What you do is simply differentiate the power with respect to t, use that derivative to multiply the exponential function itself. That gives you the derivative of the given function. So the power is t squared plus 5. If I differentiate this power with respect to t, of course, I will differentiate t squared. That will simply give me 2t. If I differentiate 5 with respect to t, 0, because 5 is a constant, there's no t attached to it. So it becomes 0, so it's off. Use this derivative now to multiply the exponential function itself, t squared plus 5. So this gives me the value of that derivative. So the y dt is simply equal to this. Also, since x is also a function of t here, it means I can differentiate x also with respect to t. And of course, the derivative of every exponential function still remains the exponential function, especially when the power is raised to actually 1 itself, when the power of the power is 1. Okay, sorry for that, but then I'm sure you know what I mean. The power of the exponential function here is t, and the power of t is actually 1. So that's what I mean by the power of the exponential function to be 1. So it remains the exponential function. But to explain this, differentiate t itself, use it to multiply the exponential function. So if I differentiate t, I will simply have 1. 1 times exponential t still remains exponential t. So still the same way, the same rule both ways. All right, so I have this. Therefore, to find the y all over the x is simply equal to the y all over the t. Now you multiply by the inverse of the x dt. And inverse of the x dt will simply give us what? The t all over the x. And this is now equal to the y dt gave us 2t exponential t squared plus 5. 2t exponential t squared plus 5 multiplied by, meanwhile the x dt gave us exponential t, therefore the inverse simply becomes 1 all over exponential t. That gives us the t dx, and this simply implies that the y all over the x is simply equal to, so this multiplied by 1 remains 2t exponential t squared plus 5 all over exponential t. That becomes the final answer to that derivative. Let's try another example and see. All right, guys, so let's say we have the question y equals cos 5t and t equals 10x squared, and we're asked to find the y dx. This also this is kind of parametric, of course, and you might want to be tempted to substitute the value of t as 10x squared in the given condition for y, so that y just becomes a direct function of x, then differentiate with respect to x. I think it can work. Let's try it and see. But then we're going to do it both ways and see. But I think it will work. All right. So if I simply put in the value of t as 10x squared, this simply becomes y is equal to, this is cos 5 in place of t. T is now 10x squared. So this is now simply saying y itself is now equal to, of course, 5 times 10 is 50. So I'll simply have cos 50 x squared. So from here now, y is a direct function of x. and I can differentiate y with respect to x, and it's simply equal to, from the rule of differentiation of trig function, differentiate the angle first, use the value of that derivative to multiply derivative of the trig function itself. So if I differentiate 50x squared, 50x squared is the angle. I'm simply going to have, of course, I'm differentiating x squared indirectly. So it becomes 2x times 50. That gives us 100x, okay? So I'll simply have 100x multiplied by the derivative of the trig function. If I differentiate cos, of course, I'll have minus sine. Okay, put back your angle 50x squared. Okay, so this simply means that the y dx is actually, of course, it becomes minus 100x sine 50x squared. So this becomes your dy dx. Well, let's try the parametric way and see if we are going to obtain the same result. I have here y is equal to cos 5t. From y equals cos 5t, it means y is a direct function of t, and as such, I can only differentiate y with respect to t. So differentiating y with respect to t, you differentiate the angle. The angle is 5t. If I differentiate 5t, of course, I will have 5. Use that 5 to multiply the derivative of the trig function itself. So I'll simply have 5 multiplied by derivative of cos 5t will give me minus sine 5t. Of course, if I differentiate cos, I'll have minus sine. So this simply implies that dy all over the t itself is now equal to minus 5 sine 5t. Keep this aside. Next, from t equals 10x squared, I can now differentiate t with respect to x because t is a direct function of x. Therefore, I can find the t all over the x, and if I differentiate t with respect to x, simply use 2 to multiply by x, it becomes 2x, and 2x times 10 will give me 20x. So this becomes derivative of t with respect to x, and from the rule or from chain rule, I know that the y dx will actually come by multiplying these two derivatives together. So I have the y dt, okay, multiplied by dt all over the x. Of course, from here, the t can cancel the t. I'm left with the y dx, and this is equal to the y dt, not forgetting, gave me minus 5 sine 5t minus 5 sine 5t multiplied by the t dx gave me 20x. Okay, so this is actually saying dy all over the x is equal to minus 5 times 20 is actually minus 100 x sine 5t, but not forgetting that t itself is actually 10x squared. So it means that dy all over the x is now equal to, this is minus 100x sine 5 times, in place of t is 10x squared times 10x squared, and of course 5 times 10 is 100. Okay, so this means dy all over the x is simply minus 100x sine 5 times 10 is 50, sorry, so it becomes 50x squared. And I think it's the same thing we obtain here. Yeah, so, and I think this is best. If the parametric function comes in this order, just go ahead and substitute the value of t into the given function, and of course differentiate y directly now with respect to x, and you have your answer instead of going through this whole rigorous exercise. All right, so one more example before we call it a quit on parametric equation. All right, guys, so finally, let's say we'll have y equals cos 5t plus sine 3t squared and x equals sine 5t plus cos 3t squared, and we are asked to find the y dx. So y is a function of t and x is also a function of t. So this is actually a parametric equation. All right, so we can differentiate y with respect to t we can also differentiate x with respect to t. So let's do that and see. Dy dt is now equal to, of course, I have to differentiate each term here with respect to t. And you know, to differentiate a trigonometric function, first of all, you differentiate the angle in front of the trig function, use that derivative to multiply the derivative of the trig function itself. That gives you the differentiation. So if I want to differentiate cos 5t, I will simply differentiate 5t, and since t is the independent variable here, and it is raised to power 1, so differentiating 5t simply gives me what? 5. So if I differentiate 5t, I will simply have 5. Use that 5 to multiply derivative of cos. If I differentiate cos, I will simply have minus sine 5t. Okay, so you put this down, plus. Now I have to differentiate 3t squared. If I differentiate t squared, of course, I will use the power 2 to multiply by t. It becomes 2t times 3. So 2 times 3 gives me 6. It becomes 6t. So you put down 60, use 60 to multiply derivative of sine. If I differentiate sine, I will simply have cos. It becomes cos. Put back the angle, 3t squared. Okay, so this now implies that dy all over the t itself is now equal to, of course, 5 times minus sine 5t gives me minus 5 sine 5t, okay, plus 60 cos 3t all squared. So you can keep this aside for dy dt. Next is to find the x all over the t. So we differentiate x with respect to t. Same thing, differentiate the angle first. Use the derivative of this angle to multiply derivative of the trig function itself. If I differentiate 5t, already explained, I will have 5. You pull down 5. Use this 5 to multiply derivative of sine. If I differentiate sine, I will simply have cos. So we have cos. Put back your angle, 5t. That becomes derivative of this function. Next is to differentiate, of course, plus. Now you differentiate cos 3t squared. So we need to now differentiate what? 3t squared, or simply t squared. If I differentiate t squared, I will have what? 2t. I will have 2t. Now use the 2 to multiply 3. That gives me 6. So you have to first of all differentiate the angle of the trig function. And the angle here is 3t squared. If I differentiate 3t squared, I will simply have 60. So I will simply put down 60. Use this value to multiply the derivative of the trig function itself. If I differentiate cos, I will have minus sine. So put it down, minus sine, put back your angle, 3t squared. So I have this. Okay, so this means that the x dt is equal to 5 cos 5t, of course, minus times 60 here gives me minus 60 sine 3t all squared. So you keep this for the x dt. So of course, to obtain the y dx is simply the y dt multiplied by inverse of the x dt. All right, so I'll simply have here the y all over the x is simply equal to the y all over dt multiplied by the dt all over the x. That's the inverse of the x dt. So I'll simply have this. All right, so dy all over the x is now equal to dy dt, give me the whole of this, minus 5 sine 5t sine 5t plus 6 cos 3t squared, 60 cos 3t squared. Okay, the whole of this multiplies by the inverse. Of course, inverse is simply dividing by the x dt, which is the whole of this value. So that's 5 cos 5t, okay, minus 60 sine 3t squared. All right, so that becomes the answer to that differentiation. All right, guys, so I hope you enjoyed this wonderful video on parametric equation differentiation. Please, if you do, and I would like to get your thoughts in the comment section. And of course, if you're new to the channel, please don't forget to hit the subscribe button to keep getting updates when much content on differentiation keeps dropping. In the next video, we are going to be talking about differentiation of the form when a constant is raised to a variable. I will see you in the next video. Thanks and cheers.